Hi everyone, this is Ming Yao from Ozin Engineering. In this video, I'll be looking at how do we make a wire thinner by pulling it through a wire die. I have the privilege of working with a wide range of companies, and it always impresses me how complex it is to make everyday things. So today we're going to look at pulling a wire through a die that looks like this. This is a Fort Wayne wire die tool. This is their blue book, so I'm going to give a quick demonstration of how we can model wire getting pulled through this die using Ansys Mechanical. So we're going to start with this, and I'm going to take a picture of it. We always need a geometry when we do analysis, so this will be my geometry. A simple picture. Then I'll start going to the Ansys Mechanical analysis system and start by creating this geometry for a static structural simulation. Okay, here is my Ansys Space Claim, a CAD modeling tool. I'm going to start by sketching on the XY plane. We're going to do an axis symmetric model, which means the Ansys would require us to have our drawing be on the XY plane, and it needs to be on the right hand side over here. So I'm going to copy and paste my picture in. You can see I can kind of carefully line it up with the background image where this line of symmetry is. I want to extract this and move it over. So I want this picture to, the actual die part, to be in this side. So I'm going to do a rotation and rotate it about, let's try to move it back into the right location here. Looks like the way I cut it, but that looks fine. So we're going to feed the wire in from this side and have the die, my diamond die over here. So I'm going to show you the whole process of doing one of these. We have an option to vectorize this image. You can see it's automatically creating a vector. We want to do the midline, and I want to maybe not include the blue part, and maybe change the threshold a little bit. There you go. So that pretty much looks like it's got a good capture of the shape of the die. Obviously, if you're using CAD tools, you can create these much more easily. So I'm going to hide my image here and select the curves. Gotta get out of my, there you go. So these are the curves I want. And copy and put the curves in there so I can get rid of the other curves. This is the only one I don't need. You can see there's a little bit of a mismatch here, so let me patch up that curve. There you go. Let's go ahead and trim out any excess over here. And that's, looks like it's a pretty good fit. So let's delete all my other curves, and then I can select all of this. And I'll use my fill button to fill it in. So now I have a surface that represents my curves. Okay, so that is the die, and the cable will go through here. I'm not a cable designer, so let's take a look at, as we go later on here, it looks like the cable should intersect maybe the middle of there's a flat section, the middle of the first angled section. So that to me is somewhere over here. So let's go ahead and do some sketching. We'll go back to sketch mode on this, and we will maybe start somewhere here and draw a cable. We're going to use the center line here, the y-axis, as the line of symmetry, and I'll go ahead and do another cable here so I have something to pull on. Trim out the excess, and I think if I hit the P button here, it'll fill that out as well. It's a pretty sharp corner. Let me round it out a little bit. So let's do a pull of, let's kind of round out that corner so it's not so extreme. Maybe 0.7 millimeters, and maybe I should pull this out a little bit too. Okay, so that is now a geometry that we can start simulating. We're going to pull this inwards. It will deform as it goes through the die. Maybe I should move this a little bit closer, perhaps. Make it a bit thinner, so that it's not quite as doesn't take quite as much force to pull this through. So let me name a few things here. So this one will be the die here, and this will be my cable, a wire. Now we can make this a two-part wire. You can make it coated with different materials and all of that, but I'm not going to do that in this example. Okay, so now let's take a look at the property of this analysis. Currently it's set as 3D. I'm going to do a 2D axis symmetric model, so I want to change my analysis type from 3D to 2D, and then go into Ansys Mechanical to set up the rest of the simulation. Okay, so we have the die and the wire. They're both oh, there we go. Plane stress. This should be an axis symmetric model. So now it's automatically going to consider this to be revolving around the y-axis. The die will be made of a diamond material. So let's see what kind of diamonds we have in our database. There's a diamond carbon. Some of these other things may have some sort of diamond information on it. And then we, for this piece, we want, let's make this platinum, pure platinum. That's the wire. Now we want to define the contacts. Normally Ansys would detect the contacts automatically, but in this case, because the gap is fairly large here, it did not automatically detect that contact. So I will define the connections. Let's have a frictional contact of this edge, and here. I guess I should include all of this. So this edge will contact, I just want this edge here, this entire green highlighted edge here. Give it a frictional value, let's say 5%, and we should be able to leave everything else automatic default. Let's take a look at the initial mesh. The initial mesh is usually fairly large, so if I generate a mesh here, we can see that's the mesh. This side probably looks okay. We don't need to have too much more detail here, but on the other side, we definitely want this piece to be more refined. One of the things we can do, I'll show you two mesh operations here. One is I'm going to put in a sizing. So the default size, I want probably at least 3 elements across. Let's switch to millimeters here so I can. So the whole thing is about 2 millimeters. So let's say 0.75 is the size of the mesh on this side. Okay, that looks a little bit better. And we can also select this. We can also put in something called inflation layers. And this allows me to select these edges. It looks like that's a little bit too sharp there. Didn't quite want to make it look like that. I'll just fill this in. And so I adjust the geometry a little bit over there to get rid of that weird little angle. And let's update the model. So one of the nice things about Ansys is that we can make changes to the geometry. It retains everything else we've set. The frictional contact is maintained. The inflation, including this part right here, and I'll do 5 layers of inflation. Because we really care about what the mesh, what the stresses and the plastic deformation looks like in the contact region. Okay. Now let's go ahead and support it. So we're going to put a fixed support on this side. We're going to start pushing this in. Insert, let's say, a displacement, and we want to make the x direction free, so this will be able to expand if needed. But in the y-axis, we want to move this up by, let's turn this a little bit. So we want to push this part all the way over here, so maybe 10 millimeters. Looks like if I do 10 millimeters, this bend will be all the way out there, so that should be okay. So move by 10 millimeters, and usually there's some sort of pull force here as well. Not sure what a reasonable pull force is, but I'll do 100 newtons in the y-axis. Maybe 20 newtons. Let's see how that works. One of the things that's helpful in this case is because there are a lot of elements that's going to be in contact and sliding, there is an detection method that's called combine. This checks for all the different contact possibilities, which makes it easier to detect when contacts happen. And finally, this will be a large deflection problem, and we're going to turn on automatic time steps. So we're going to start with let's say 100 sub-steps, and then we're going to let it run to take very small sub-steps. This allows us to make sure we get convergence by updating the simulation. If it fails to converge, it will update the analysis and rerun it from the last converged solution with a smaller deflection. So it's off and running. We can look at the force convergence history. This tells us how well the model is converging. Looks like converging very nicely. So it's already 40% of the way in, which means it's gone through 4 millimeters or so. And we can see that it's, maybe I should have made it a little bit thicker. This looks like it's not really doing much interesting things here. Maybe making it a little bit. We can look at the material properties. Ansys does have plus plasticity curves for many metals. For diamond, it's just a linear elastic curve, but we do have a temperature-dependent thermal expansion coefficient. For platinum, we do have a plasticity curve, so this is including metal plasticity in the model. Okay, so it's making my metal slightly, my wire slightly thinner. Okay, it's at 87% here. Okay, so now once it's finished, we can look at lots of things. We can look at stress. We can look at strain. I want to see the plastic strain as well as the total strain. Let's grab all of those results and take a look. So the deformation makes sense. As it goes through the die, it flattens out and makes it slightly smaller. Equivalent stress, we can see the stress builds up. Plastic strain, so there's permanent deformation in this region. And then total strain. So that all makes pretty good sense. You can see this is running on my 6-core laptop. That's about 5 years old, and the whole simulation time, I think there's solution statistics here. So let's see, it took a minute and 36 seconds to solve. It's a very small model, so these are very good models to learn analysis, nonlinear simulations. But it's not really very interesting if it only moves a little bit. So let's adjust the geometry a little bit and see what happens if I move my wire, make it thicker. So geometry has been adjusted. I update geometry from source. I hit solve, and it automatically meshes based on the previous settings and starts solving this new simulation with a much thicker wire. Let's go back to looking at convergence history, 13%. So we're still cranking through this very nicely. Maybe platinum is a fairly soft metal, so it's not. Let's see if I can show also, there's a stress plot tracker and a strain one. These will be much more interesting, I think. So we can get the results as we're solving. Okay, yeah, so it's much higher strain here as we try to push this through the top. Still converging very well though. Okay, much higher deformation. It's almost done here, 87%. Okay, let's run the simulation. We can see the way the part deforms now. You can see the part swelling up on the back as we try to push this wire through the die. Let me turn off my contours here. Equivalent stress. So initially the stress is very low, or relatively low, but then when this corner hits, it kind of bites into the wire, and then we get all kinds of problems. Plastic strain. Same thing, once we get past this little corner, things kind of go wrong in this wire pulling example. And total strain. We can also figure out how much force it takes to push this through just by dragging the displacement into the solution and evaluating the force. So initially it's taking about a few hundred newtons, but as we pull it in, because of the way this part thickens up over time, the force increases as it expands, the metal gets built up in the back. So maybe I need to have a stronger force pulling on it. One of the important parts of Ansys is that we are able to make everything a parameter. So I can make the pull force a parameter. I can go in here and make the thickness of my wire a parameter by clicking on this P. And now I could do a parametric analysis. I can, for example, go to my simulation and start making results parameters too. So maximum stress may be a parameter, maximum plastic strain could be a parameter, force reaction total can be a parameter, and now I can do a wide range of design optimization studies to try to figure out the right parameters I need for this particular die if I want to do different thickness of wires with different force or pull conditions. Hopefully that's helpful. There's a lot more capability. I'll try to include a few more in future videos, but thank you very much for your interest in this model. I thought it was very helpful for some of our customers and prospects to be able to do this type of simulation. Although I'm not a wire pulling expert, the tools can be used for this industry, and it's really easy to solve since it's a 2D axisymmetric example. Hope you enjoyed the video. If you like this, please like us on YouTube and subscribe to our YouTube channel. If you have any questions, reach out to us at ozeninc.com. Thank you and have a good day.